through. So this is the just-in-time PD for intermediate math, spatial science, and measurement. Just a reminder, Rhonda is going to start recording this session just so that you know that up front. And our topics for today under measurement, grade 7, we're looking at circles and cylinders. Grade 8, we're actually looking at circles and cylinders as well, but through the lens of area and volume. Okay. So this is our teaching and learning support staff. We have our primary folks, our junior folks, and tonight our intermediate people. So my name is Lene Bates, and I'm sure many of you are also familiar with Rhonda, who's here with us this evening. She's going to monitor the chat. So if you put any comments or questions in the chat, she's going to interject as often as necessary. So what we're looking at here is, of course, the long-range plans that you may be familiar with on the website. So this is the grade 7 spatial sense circles and cylinders long-range plan. So probably where most of you are is where that yellow arrow is, that you're probably doing algebra, patterns, and relationships right now. There is a 3-day sort of buffer zone in there. So you do have a little bit of wiggle room, of course, whereas, again, we're looking at the April coming next week. And after that April break, we're, of course, hoping that everybody will be ready to start the spatial sense unit, which is measurement, and in grade 7 is focused on circles and cylinders. The grade 8 long-range plans look very similar, of course. So again, hopefully everybody at this point is in their patterns and relationships unit, and that you do have a little bit of a buffer zone there before the April break next week, and then everybody starting off with their spatial sense measurement unit. And in grade 8, the focus is on area and volume, but we'll talk about some of the prerequisites that are needed for that coming up. So today's agenda, we're going to do some talking about prerequisite knowledge that is needed for both the grade 7 and the grade 8 measurement unit. We're going to connect the cluster of expectations that you will see on the long range plan. So there's some number expectations as well as some algebra expectations. We'll of course move into the new measurement expectations, and then as well look at some resources that may be helpful to you. So when we look at this, it looks like a lot of expectations. So this is just a screenshot from the long range plans of the cluster of expectations that we would be looking at, and this is the grade 7 cluster of expectations. So you'll notice that we did a bit of color coding here. So the blue box actually goes around any number expectations that we'll be looking at in this particular unit. The orange box is the algebra expectations that we'll be revisiting during this topic. And the green box, being our spatial sense color, is the measurement expectations that we'll be looking at in this topic. We'll look at each of these in a lot more depth, so don't worry about it if you can't take in this massive cluster of expectations all at once right now. So when we look at, now I'm looking at just the green box of expectations, so the measurement expectations, and you'll notice that the title here says new to grade 7 and grade 8 in 2020 and 2021. So of course our grade 8s this year did not do circle and cylinder as a measurement topic last year. So this year we're asking the grade 7s and the grade 8s to do the circles and cylinders expectations within measurement. So you'll notice that what we've done here is bolded the expectations that are brand new to the students this year. And the ones that are not bolded are expectations that we'll just be revisiting. So if we look at the first bolded expectations, Then we'll be describing and classifying cylinders. Now in grade 7, you already did this with pyramids and prisms, but the fact that we're looking at cylinders is obviously new to this topic. The other new topics, if you look at 2.3, is looking at the relationships between the radius, the diameter, and the circumference of a circle and solving related problems to that. 2.4 is constructing circles. 2.5 is looking at the relationship between the radius, the diameter, and the area of a circle and solving those related problems. 2.6 is representing cylinders as nets and determining the surface area of a cylinder. And 2.7 is looking at the volume of a cylinder. You'll note there that you've already discussed volume with prisms, but we'll be looking at all the relationships between the dimensions when solving problems regarding cylinders. The 3 topics in the middle there that are not bolded are topics that you've looked at, or are expectations, sorry, that you've looked at in other topics this year, whether it is looking at drawing perspectives from different views. And obviously in this case, we would be doing that with cylinders. And then of course, describing the similarities and the difference between volume and capacity, in this case, looking at cylinders. And of course, you will be discussing with students the differences between solving problems that involve perimeter, area, and volume. So now digging deeper into the cluster of expectations that are not measurement. So the blue box again is our number expectations. The only new number expectation for our grade 7s is identifying and representing perfect squares and determining their square roots. Grade 8s this year, you will have already worked on that a little bit in the Pythagorean relationship. All of the other expectations there are ones that you have already done this year, and we'll dig into those a little bit deeper in some upcoming activities. Just a special note for grade 8s. So these are the expectations that you'll notice are new to grade 8 that you will, in some cases, possibly be addressing in more depth in the next school year, 2021-22. However, these new expectations you could probably address this year through the lens of circles and cylinders. So 1.2, when it's talking about making models, you could do that through the lens of circles and cylinders. 1.3, doing scale drawings and looking at the different ratios. Again, you could do that through the lens of circles and cylinders. And of course, if you have time, 2.3 at the bottom there is looking at solving problems involving perimeter, area, volume, and circumference, of course, of composite 2-dimensional shapes and 3-dimensional objects. So that might be something you can look at if you find that you do have some extra time. Okay, so today's agenda. We're going to look at we just finished looking at the prerequisite knowledge that you need to have in grade 7 and grade 8. We're actually going to jump into looking at some of those connection pieces. So the number expectations and the algebraic reasoning expectations, we really want to focus on those always because of those 4 non-negotiables. So first one we're going to look at is some number expectations. So we talked about the fact that in grade 7, that identifying the perfect squares and square roots is new information. For grade 8s, not so much. And that students may have to use their rounding skills as well when they're looking at some of those concepts. So we're going to dive into an activity that looks at how you could address this. So when we're looking at perfect squares and square roots, it's probably a great opportunity to look at that using number talks. So there's a couple of links here that are from Andrew Stadel. Some of you might be familiar with doing some clothesline activities in other topics that he's done. So the first link there is actually some printable cards that you can use to do the activity that we're going to delve into in just a little bit. The second link is actually a link to his blog, which goes step by step through this clothesline activity. And the third link there is a very similar activity that you could do using Desmos, especially for our distance learning teachers, and of course our in-person learning teachers as well. So in a second here, Rhonda's going to put the link to this activity in the chat. We're going to try out this activity called the double clothesline activity. And I'm just going to go to it here as well. So you should be, once you get the link, it's just a link to a separate slide deck that we're going to play around with a little bit here. Just give everybody a second to get there. Okay, so what you're going to notice about this activity is there's a different slide there for each person to play around with. Basically, it's a double clothesline activity for people who haven't done it before. So there's sort of the two strings that are strung up that teachers could string up in their classrooms. The bottom string is just those yellow, sort of, it's a number line 1 to 10. You can't actually move those particular cards. But the cards that are gray above, you can move those cards to a spot that you think lines up directly with numbers 1 to 10 below. So you notice that the cards are visual. So they show, you know, a square root with an actual square underneath. Some of them have the numbers involved. Some of it's just the visual. We always like to keep it visual for our students. You'll also notice that the cards there is perfect squares that are represented. So they will line up with a whole number below. Whereas grade 8s, on the other hand, they have to sometimes, in the expectations, they have to estimate square roots that could be a decimal. So just to note that, grade 7 teachers, you would only actually be using cards from the activity that are perfect squares. Grade 8s, there is an expectation that they can approximate. So I'll let you play around with that for a few minutes. And if you're not familiar with the double clothesline activity, feel free to look at anybody else's slide in the slide deck as well. That's what this is intended for. It's sort of like non-permanent vertical surfaces that you can see what the other students are doing. Awesome. So I can see that people are moving the gray perfect squares or square root cards around, try to line up with the numbers below. And as I said, if you're not sure what to do with the activity, feel free to look at the other people's slides as well and see what they're doing, trying to put those perfect squares on the top line. Awesome. Okay, we'll give you about 1 more minute to play around with that. Great. I see lots of you are making a lot of progress here. Okay. Awesome. So it's okay if you didn't get the activity finished. You kind of get the idea here of what you're looking at. So I'm just wondering, going down the slides here, I want to consolidate things a little bit. So there's some people obviously that have a whole bunch of them placed on the clothesline. I'm wondering if somebody would be willing to unmute and talk about how they decided where one of the cards should go that was not a perfect square. So let's say specifically the square root of 12 is one of the cards that's there that's not a perfect square. I'm wondering if somebody could unmute and talk to us about how they decided where it would go. Is there anybody who'd be willing to do that? I'm not sure if anybody's putting it in the chat. Are they, Rhonda?
No.
Okay, I'll jump in.
Okay, Jeremy.
There you go. We actually worked on this today. So basically you find the perfect square before and after 12. So the perfect square before 12 is 9. So the square root of 9 is 3. And then you find the perfect square after 12, which is 16. And square root of 16 is 4. So you're looking at the answer between 3 and 4. Because 12 is slightly closer to the 9 than it is to the 16. It's roughly going to be like 3.4, something like that, pretty close to middle. So you're looking at a spot somewhere between the middle. So for us, like in our class today, we were just looking at perfect squares. We weren't quite into the partial ones just yet, like the ones that are not perfect squares. That's kind of what we're going to work on tomorrow.
Awesome. Thanks, Jamie. Perfect timing that was something you just did in your class.
Yep.
Okay, and Jamie also highlighted sort of difficulties that students might run into there. I'm wondering if anybody else, whether it's in the chat or if you can unmute your mic, why might an activity like this be helpful for consolidating ideas like this for your students? Why an activity like this? What would be helpful?
Can I talk?
Sure, go ahead.
Okay. I was just going to say, for me, we just actually looked at perfect squares too. And I think for me, it helps the kids give a better understanding when it isn't a perfect square to find those two values where it would be in between. So you get an idea of, for me, as an answer, so that they know when they get an answer, yeah, that's got to be right because I know it has to be between 3 and 4. So when they get an answer like 7, they're like, okay, that can't be because it doesn't make sense. So given sort of maybe just a better understanding of what the actual value means in order to help them making sure that they're getting a proper answer in the end.
Awesome. Yeah, excellent. And it's helpful for them to be able to see that, right? To have it very visual. So listening to both of you talk about that, it's very helpful for them to be able to see where exactly they would fit on a number line. Awesome. Okay. Actually, I am going to back up a little bit there as well. Just for teachers who haven't done any double clothesline activities before, if you click on that second link there, there's a blog that sort of takes you through this activity step by step. So if that's something you're interested in, then for sure have a look at that. Okay. Okay, now looking back at our cluster of expectations again, another set of number expectations have to do with proportional reasoning. So we're going to look at how you might delve into that as well. So with our grade 7s and our grade 8s, they probably are not familiar with anything that has to do with a circle at this point. So you would obviously want to start out with some sort of visual representation of a circle and introducing them to that important vocabulary. So circumference being the perimeter of a circle, talking to them about the radius, that the radius is the measurement from the center of a circle to any point on the outside of the circle, and that the diameter is the measurement of a point on the outside of the circle going through the center, going through to another point on the outside of the circle. Typically, we want students to do some inquiry into the relationship between these dimensions and these calculations. So in a class, you would typically get some circular objects. Teachers hand out a piece of string and have students use the string to measure the circumference of the circle, place it on a ruler, as well as measure the diameter of a circle. Given our context today, what I would see that happening more like is maybe brainstorming with students a circular object, one circular object they may have at their desk, handing out that piece of string to them and getting them to investigate that relationship between the circumference and the diameter, and maybe having a whole class chart at the front of the class where you can record objects, their circumference and their diameter, so that students could start to see some of those patterns. So you can see there's a table there that you could list the different objects, list the circumference and the diameter. In order for students to see what relationships are important there, you'll see that there's 3 other headings at the top that have not been filled in. Is there anything you can think of that might be a helpful calculation for students to do involving circumference and diameter that could help them see the relationship between the diameter and the circumference? So is there any sort of calculation operation we could do using diameter, using circumference, that would help students start to see the proportional relationship between those two? You can feel free to unmute or put that in the chat.
Hi, Lene. This is your chat. This is the chat talking.
Okay.
Steven says radius. Brad says division. And Trisha says C:D. Steven then also says pi, ?
Okay, awesome. So I'm going to enter some things here.
Kevin added C div D. I think that means divided by D.
Yeah, so C divided by D would obviously be very helpful in terms of seeing that proportional relationship, that the circumference is 3.14 times, or approximately 3 times the diameter. I think you also mentioned a ratio, didn't you, Rhonda?
I did, yes. Trisha did C:D.
Yeah, C:D obviously as well would be amazing to see that actual proportion relationship. And what was the third one?
We had a pi, ? And C div D. I cracked that code. C divided by D.
Awesome. So the pi is of course what we're trying to get to. So yes, exactly. That's exactly what we're trying to do, is we're trying to get them to see that relationship there. A question that I had as well is, I'm wondering what some experienced classroom teachers, what sort of activities they've done in their class with those concrete objects. So I suggested, you know, taking the circular object at their desk with a piece of string, measuring those. Are there some other concrete activities that teachers have done in their classrooms?
I did an activity where I took a square and I had them take another colored piece of paper and we folded it into a circle. Oh, sorry, we were talking about, no, I did that for area. Sorry, not for circumference.
Okay, that's okay.
And we just took we sort of cut off the corners of the square and we glued the circle on top of the square. And then I took another square of a different color and they folded it and I made it come to a diagonal of a smaller square and then they put that on top and then I had them cut it into 4 and then each person in the group, because there's 4 in a group, had that. We looked at the relationship then. We were talking about area of a circle and how it relates to area of a square. So that relationship of pi and the the circle covering 3.14 out of the 4 squares. So we had done that one for area.
Awesome. Yeah, and what we typically want to do when we can, of course, is do that sort of concrete representation before we would move to, use a concrete object before we would move to some sort of representation and then to the abstract. So if you're not able to do a lot of concrete examples in the classroom, maybe 1 or 2, and then move to a more abstract representations, you'll notice that there's a couple of links on that particular slide. So GeoGebra has a great activity where they roll a circle and they can see how the diameter is related to the circumference. And there's a Gizmos activity too there that's great to do that with.
Just to add, Lene, Scott put in the chat, we have measured the circumference and diameter of car tires.
Oh, I love that. Yes. I saw that online actually, where they had a car tire where they were actually rolling it across the parking lot in a school. Yeah, that's awesome. Okay, so you'll see on the next slide, it's just making it really explicit then to your students what that proportional relationship is. So in that first in that first ratio table, we have that example of the radius being 4, the diameter being double your radius being 8, and how you could use that to figure out, of course, what the diameter would be when the radius is 2.5. We have the other ratio table below there too that sort of shows students the proportional relationship between the diameter and the circumference. And Rhonda and I talked a little bit here about whether we wanted to use the pi symbol or use an actual decimal for circumference. Depending on what students are using for their calculators, whether they're punching in 3.14 or they have an actual pi symbol, then they're getting slightly different answers. So it might be beneficial for them to see it this way as well and understand sort of in the bottom here that when the circumference is 15, then the diameter would be 15 divided by pi. So you can use those ratio tables to really hammer home that proportional reasoning. This is another example. So one of the other expectations was that number expectation was that students could convert metric measurements. So this is a would you rather activity. Would you rather have a pool that is on the left, the dimensions in meters, or the pool on the right, the dimensions in centimeters? So students would have to do some metric conversions in order to figure that out. We of course want to make those metric conversions really visual as well. So you'll notice the table on the left there, it's going from meters to centimeters. The middle column really has that visual representation for students. So for example, when we look at area, that 1 meter squared, if we're looking at it in centimeters, is 100 centimeters times 100 centimeters, making it 10,000 centimeters squared in the end. Again, Rhonda and I talked about it'd be great if you could actually have the concrete representation first, if you were able to even use a meter stick or find a YouTube video that would allow students to be able to visualize before they move to the representation in the abstract. And then, of course, you have your ratio tables off to the right there as well. So a ratio table for linear measurements, a separate ratio table for area or 2D measurements, and a separate ratio table for our 3D or volume measurements. Okay. Again, when we're looking at our cluster of expectations, now in the orange box, we're looking at algebra. So there's nothing new here for our students, whether it's grade 7 or grade 8. They have previously looked at evaluating algebraic expressions. They have also previously looked at solving equations. So this is revisiting and making those connections for them. The lovely Marion Small, in one of her topic videos in algebra, she makes it very clear the connection, and we want to make the connection clear for students too, that their measurement formulas are actually just using algebraic reasoning. So she wants to connect for students the 4 principles that are there. So the first one, that solving algebraic calculations or formulas in this case is just exactly the same thing as simplifying numerical calculations. Number 2, that algebraic notation just simplifies communication for everybody, that everybody's using that common language, so the dimensions, etc. Number 3, that algebra or the formula can decontextualize a specific situation. So when looking at a specific situation, we can recognize, oh, we're actually just looking at diameter, or we're actually just looking at circumference. And then conversely, number 4 there, that when you're using an algebraic equation, it can also represent several different situations, which can be helpful for students to understand. Okay, next here we actually have a diagnostic that is suggested by Marion Small. We're going to go through this diagnostic kind of quickly, only because we're going to revisit it a little bit in the end. But I'm wondering if anybody can tell me what you notice about this diagnostic. So this is a diagnostic that is meant to do before this particular measurement unit on circles and cylinders. So I'm just going to let you have a look at the first 2 questions there. And then I'm going to show you a couple more questions as well. They're choosing a number between 20 and 30. They're sketching a parallelogram, a triangle, and a rectangle, that each of those has the area of the predetermined number. Question 4, then they're being asked to sketch a square with a perimeter in meters of that same value. Number 5, what would their perimeter be if they were doing it in centimeters as opposed to meters? And number 6, how does the perimeter of a square compare to the side length? So my question is the following: why ask these particular questions as a diagnostic for this topic? Does anybody have any ideas about that? You can unmute or put it in the chat. Either is great.
I guess because in the parallelogram, you can break it down and you can get that triangle, and then you can also get the square in there as well if you kind of dissect it.
Definitely. You can start to see the relationships between those 3 shapes for sure. Anything else anybody's noticing?
I was going to say, if you know the area, then you probably could figure out the perimeter by using square roots. There's a relationship between the squares and that square root to find the side length.
Definitely. That's exactly what we're hammering home, right? Is what both of you said, the relationships between the different dimensions, the different shapes, and the algebra. So you'll notice that this diagnostic doesn't have anything in it about circles and cylinders, because our students don't know anything about circles and cylinders yet. So really, we're just looking at how they can manipulate the algebra in formulas. So if we look at this next slide here, these are the diagnostic look-fors that Marion Small identified for this particular activity. So even though this is a measurement diagnostic, you'll notice that the first two look-fors are actually more of an algebraic sort of understanding, that they can manipulate between the shapes, the dimensions, the calculations, as you mentioned. And the bottom two are actually more sort of number expectations in terms of conversions between metric units and looking at those ratios, the proportional reasoning. So we've looked at the prerequisite knowledge needed. We've looked at some of the connections that can be made between this measurement unit and number expectations along with algebraic reasoning. So now we're going to look at the specific measurement expectations with circles and cylinders. So we've already looked at this, that within our measurement expectations, we have quite a few new ones, and they have to do with the circles and cylinders. And we're going to try an activity where we're going to look at some of the relationships between the different dimensions in circles and cylinders and how they are related to each other. So there's two activities on this slide. We're actually only going to talk about one of them, but it is a 3-act math task. So some of you may be familiar with doing those 3-act math tasks. And what we're going to ask you to do is actually go into some breakout groups at different stages in this 3-act math task. So I'm going to show you a slight video just to set up the first act of the problem. Then I'll explain to you what I would like you to do in your breakout groups and sort of different roles that you can take. And we'll come back and forth between each part in the 3-act math task. So I'm going to just play the video for you first to introduce the first act of the problem. There is no volume in the video, so don't feel like you're not hearing something. It's just something visual for you to look at. Okay, so we've had the introduction of this particular problem, that would you rather, because it is a would you rather question as well, have 2 12-inch medium pizzas or 1 18-inch large pizza? Now, when you do go into your breakout groups in a moment to discuss this, you will want to talk about first, obviously, what you notice about the problem so far, what you wonder, what information you think that you still need in order to make this determination. Also, when you do go into your groups, what I'll do is ask you to take on a particular role in your group. So we would need sort of somebody who is monitoring the time. So you're going to have 5 minutes for each act of this 3-act math problem. Somebody who's the facilitator, who sort of, keeps track of the conversation. Somebody that records the group's thinking. So the slide deck that we had before with the clothesline activity, you'll notice at the end, there are some slides for you to record your group's thinking. Or if somebody just wants to jot down things on a piece of paper, that's fine too. Or if your group just wants to share your thinking orally after each act of this math task, that's fine too. So you do probably want to come up with a spokesperson as well. So in a moment, I'm going to send you into a breakout group for 5 minutes to first just discuss this first part. So you want to have a facilitator, you want to have a timekeeper, you want to have somebody who records the group's thinking, and a spokesperson as well. Okay, so I'm going to go into...
I have rooms ready, Lene, if you want.
Oh, you do? That would be amazing.
Okay.
Thanks, Rhonda.
You're welcome.
Okay, I'm gonna stop sharing just for a second, only because then I can see you in terms of our consolidation. So I would always want to hear what some of your conversations were about. So I do want to hear some consolidation. We may not have time to hear from every group, but is there a spokesperson that would like to speak to for their group in terms of the conversations you were having?
It's a great topic. I've done this before, not so much with pizzas. Like before, we had to do circles in grade 7. I did rectangular pizzas, kind of thing. Same sort of idea. Which one, or trapezoidal, or whatever you want to, whatever shape you want to do. We were just talking as a group how it's a good activity because everybody's hungry, and this is probably really awesome right before lunchtime, or one of the nutrition breaks. So everyone has kind of an opinion on this in terms of food is a pretty easy one to kind of go after. The other thing too is just you can make it really relatable in terms of the prices. So if you wanted to extend this, you could actually give prices to these pizzas and then kind of have them go there as an extension. What are you trying to find? The other thing, like in terms of what are we talking about? Are we talking about perimeter? Are we talking about area? So having the kids to decide what is this question actually asking in terms of the math that's involved, and then again, just which is the better deal we kind of talked about as well. If you want to extend it on, beyond that.
Awesome. I love how you made it so real life and relevant for the students with pricing. And Rhonda mentioned too, that's a great way to revisit decimals. And then it's a perfect segue into the next part, what you were mentioning about, well, what are we talking about? Are we talking about area of the pizza or the crust of the pizza, or what's the most important thing to do there? Yeah, definitely a great way to introduce circumference and area. Okay, so I'm gonna present again so we can look at the next part. Okay, so we're gonna look at the video again. Okay, so just as Jamie was just mentioning, so now the question is, what if you want the most crust? So we're going to send you back into your breakout groups again. This time we're only going to go for 3 minutes because we are running out of time, but discuss the math behind what if you were looking at you wanted the most crust. I don't know who wants the most crust, but so Rhonda's going to send you back into your breakout groups now for 3 minutes. Okay, so we're trying to do some consolidation here. I'm interested to hear, is there maybe a spokesperson from this time that can talk about your thinking about that act? So what sorts of different conversations did you have that time when they were specifically asking about the crust as opposed to just which one would you rather? You can unmute or you can put things in the chat. That's great as well.
What we were thinking about is more of like the tactile kinesthetic way that you can do this with your students. So, and maybe using that piece of string, trying to measure it out, maybe seeing how that piece of string could be related to the 2 different equations for circumference.
Okay.
And seeing how it could be attached, and then we're even talking about using a wheel and like measuring it out and seeing a 1 whole rotation, how far that would get you, as well as a means of measurement is too.
Amazing. I love how you're sort of connecting the concrete and the representations in the abstract. Awesome. Okay, what I'm actually going to do is show you the consolidation that they provide in this actual video, because it's a really good consolidation to do with your students as well. So I'm just going to go back to sharing my screen here. Okay. So you're going to see how they consolidate this particular part of the problem. You can see very clearly how they're using the visual there of 3.14 groups of the diameter making up the circumference and using that pi symbol. Then doing the same with the larger pizza. And then, of course, showing which one is clearly the winner in terms of which one has more crust. Okay, what we'll do now too is I will introduce the third act, which obviously has more to do with area. We may consolidate that one a little bit differently, but you would always want to consolidate with your classes in the end. They're thinking about each act of the 3-act math task. So I'm going to show you one more part. Okay, so this part, slightly different question. Not as what if you want the most crust, but this one, what if you want the most pizza? So once again, Rhonda's going to send you into your breakout groups for 3 minutes, and you can discuss this part of the 3-act math problem. Okay, awesome. Normally, as I said, what we would do now is we would listen to the conversation that you were having so we could consolidate that. However, I really want to respect your time. I'm already noticing that it's 5 o'clock. So we're just going to go about 3 minutes over to show you some resources in the end, but also to let you know in that video itself, they do, again, an awesome consolidation of why the area formula works the way it does. So I assume many of you were talking about how to look at the area of those pizzas in that particular demonstration. So I'm going to